Okay, welcome to this next video. What we're going to do here is we're going to have a look at the three different number systems and all of the different things you need to be able to do with them in your exam. Okay, I know it's not a great shot. There's reflections from the window and all sorts of things making it difficult. So at the end of the clip, I'm going to move the camera closer and just take you around everything again so you get a closer look at it. Okay, what I started off with here is just the basics. Okay, we've got base 2, base 10, and base 16. Otherwise known as binary, denary and hexadecimal. And each one has got a different number of numbers in it. So in base 2 you've got 2 numbers, 0 and 1. Base 10 you've got 10 numbers. And in base 16 you've got 16 numbers. Going from 0 all the way to F. And just in case you don't recall or you get a little confused with this, the A there, that's worth 10. The C, that's worth 12. The E is worth 14. And hopefully you can work out what the others are. So those are the basics and the key things that you need to know about those numbers. Okay. Now the reason that obviously we use denary as humans is because we have 10 fingers or 10 digits. We've got 8 fingers and 2 thumbs. That gives us 10. And so it's sort of natural that we came up with a system based around the number 10. With computers, which are basically made up of transistors and switches that are either on or off, they only function in base 2. Where something is off or on, 0 or 1. So everything that the computer does, stores, or whatever you want to call it, is represented with a 1 and a 0. It's represented as a binary number. Now we've learned about this in different ways in class. So we've talked about pixels in images being encoded, and a 2 to the power of 2 pixel would be 2 times 2, 4 different possible colours. We know from sound files, that there are bits that are being stored to represent the sound, and we've talked about the formula for working out the file size there. We know from the ASCII table and the extended ASCII table that, again, binary numbers are used to represent every single character and space and symbol on the keyboard. So it's every single thing that the computer does. And again with storage devices, but more on that on another video. So once you've got the basics here, some of the things you might be asked to do in your exam, some basic things to start with might be converting from one number system to another. Okay, so typically a question like this might be, well, here's a binary number. So we're going to write an 8-bit binary number. Remember, each number is a bit. 4 numbers is a nibble, or 4 bits is a nibble, sorry. And then when you've got the full complement of 8, you've got 1 byte of data right there. Okay, the next thing you need to do is you need to know the place values of those digits. Okay, so I'm going to go for a bit of green on this one. The place values, always starting with the units column. Then we've got the 2 column, the 4, the 8, the 16, the 32, the 64. And I've obviously missed the digit off there. There wasn't 8, now there is. So now I've got my full byte, 8 bits in a byte, and 128. Now then, you might be asked to convert that to base 10. That's very simple to do. You have a look at where the 1s are. We've got a 64, an 8 and a 2. And you should be able to work out fairly quickly that that must be 74. Because 1 times 64 is 64, 1 times 8 is 8, and 1 times 2 is 2. Add the answers together and you get 74. That's fairly straightforward. Another thing you might be asked to do in an exam is to take a base 10 number and convert it to base 2. Okay, so that's fairly simple to do as well. This time we'll work backwards. So if we start off with the number 50, okay, and what I'm going to do this time is I'm going to write down the place values first. Okay, so I'm going to need my units, my 2, my 4, an 8, a 16 and a 32. I won't need 64 because that's bigger than 50, so I don't need to use it. Okay, but well, we'll come back to that in a second. So let's write down the number 50, starting with the highest place value. And I need to make 18, because 50 take away 32 is 18. So I'm going to need the 16. That leaves me needing 2, so I don't need an 8, I don't need a 4, but I do need that 2, and I don't need a 1, and that gives me 50. Now, it's good practice to present your answer in 8-bit notation, so that means we do need those other zeros just there. And we know that if the place values were on those, it would be 64 and 1, 2, 8. Okay, so that's converting from base 2 to base 10 and back again. Now, what you might be asked to do though is to work with a hexadecimal number instead. And usually you'll be asked to convert your hexadecimal number to base 2 or possibly to base 10. So here's how you do both. Alright, first of all, if we take that 74 again and bring it over here. So we've got 0, 1, 0, 0, 1, 0, 1, 0. Okay. Now then, first of all, let's convert it to base 2 because strangely that's easier to do. Okay. So if we're converting that to base 2, there's a simple way you can do this, and it works really nicely when you've got an 8-bit notation number. Okay. So what I'm going to do is I'm going to split the number, the 8 bits there, in half, into 2 nibbles. And I'm going to deal with this one and this one separately. Okay. Because of that imaginary line, we're going to do 1, 2, 4 and 8. And then on the other side of the line, we're going to do 1, 2, 4 and 8 again. Okay, you'll see why in a moment, hopefully. So, on this side we've got an 8 and a 2, which is 10. Now in base 2, we know that 10 is an A. So that side will be A. Okay, and then here, 1, 2, 4. So that side is a 4. We'll put a 4 there. Put those 2 numbers next to each other, and 4A is the hexadecimal version of that. Now, if you think, well, that can't possibly work, let's check it out. Let's convert that number now back to base 10. So, because this is base 16, we've got our units column, and the next one along, 1 times 16, is the 16 column. So this number here is really worth 4 times 16. Okay, now I'm not going to do that in my head and get it wrong, so I'll just quickly here do that. So 4 times 6, 6, 12, 18, 24. Put my 2 there, my 4 there. 4 times 1 is 4. Add that 2, gives me my 64. So that 4 there is actually worth 64. Okay, the A there in the units column is 10 times 1, which equals 10. And my 64 and my 10, when you add those together, equals 74. So you can see the system works. It's nice and simple. Okay, and it works the other way as well. So you might be given a hexadecimal number. Say, for example, you're given F2. Okay, you can do exactly the same thing, but in the opposite direction. So deal with it one bit at a time. The F is 1, 1, 1, 1. The 2 is 0, 0, 1, 0. And there's your answer right there. You don't need a calculator, you don't need to convert to base 10 first, and you can do it almost entirely in your head. It's very, very quick and easy to do. So those are some simple calculations from one base to another, and with practice they should become very quick, easy marks to get. And on the second mock exam that we did this year, you know, there were 4 or 5 marks available for this, and we know that 4 or 5 marks is getting you close to 5%. 4 marks is about 5%, which is, you know, between some grade boundaries is half a grade. Further up, it's almost an entire grade difference just on 5 or 6 marks. So it's really important. Okay, another thing you might be asked to do is to do some binary addition. Now these sorts of questions can come up in lots of different ways. You might just be given 2 binary numbers, like these 2 here, for example. Okay, you might just be asked to add them together. It might be as simple as that. And if it is, then it's your lucky day, because all you're doing is adding 1s and 0s, and it couldn't be simpler. Okay, now, let's add them together, and then we'll check the answer at the end. Okay, a couple of things you need to remember when adding binary numbers together. Okay, you're writing the answer. The answer will always be a 1 or a 0 underneath. Okay, so what I like to do, just to help me out when I'm doing this, is I like to remind myself of just some basic answers. Okay, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 1 is 2, written as 1, 0, don't forget. Okay, and then I'm just going to do one more, so 3 is 1, 1, and so on and so on. Okay, now then, as we go through this question here, and I'm just getting a different colour, 0 plus 0 is obviously 0, 1 plus 1 is 2, written as 1, 0, so we put the 0 there, and we carry the 1. Then we add that one up there, that's a 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 0 is 1, and 0 plus 0 is 0. And there's our answer. Now, we know from looking at this that 50 plus 74 is 124. Okay, let's check what that number works out as when we convert it back to base 10 and see if we've got our maths right. So we've got the 1 column, the 2, the 4, the 8, the 16, the 32, and the 64. So if we do 64 and 32 and 16 and 8 and 4 and add those together, let's see what we get. So in the first column there we've got 24, carry the 2, 6, 7, 8, 9, 10, 11, 12, 124. 50 plus 74 is 124. So it works. It's nice and simple. That helps. It helps me every single time, and it's useful to have it there. Another thing you might be asked to do is to do some binary shifts. And so this is where we start doing some multiplication and division by powers of 2. Okay, and there's simple things to remember here that will help you make sure you get it right every single time. So, it's most likely going to be the case in your exam or in a mock exam or whatever that you are asked to multiply by 2, maybe by 4, maybe by 8. Okay, so let's just figure out how we do that. So multiply by 2, multiply by 4, multiply by 8. Okay, you might even go up to 16, although it's possibly less likely. So why is it those numbers there, not by 5 or by 7? Well, the reason is because of the number 2. These are all powers of 2. So 2 to the power of 1 is the same as multiplying by 2. 2 to the power of 2 is the same as multiplying by 4. 2 to the power of 3 and 2 to the power of 4 and so on. Okay, so that's why it's that system. And it's the power that's really helpful and really important. Okay, because that there tells you how many shifts you need to make when doing your binary shifts. So, if we start off with a simple number so that we can check that this works, let's do the number 10. Okay, so we know that the number 10 looks like this. Okay, and that equals 10. Now then, if I want to multiply that by 2 and get 20, I need to do a logical shift. To multiply by 2, I need to do 2 to the power of 1. So it's one shift, and if you're multiplying, you're shifting to the left. Okay? Shifting to the left to multiply, shifting to the right to divide. So if I shift all of those numbers up one, okay, this is what I'm going to get. So I'll start it from this side, so it's 0, 0, 0, 1, 0, 1, 0. And now, in this column here, I'll replace it with another 0. Now, if we put our place values on there and just check this, okay, and I don't need to go beyond that because the rest are zeros. 8 add 2 is 10, 16 add 4 is 20. So we know the system works. It works the other way if you're dividing as well, so we'll just go for a completely random number here to test out division. Okay, and you can see there, just to be clear, because we've multiplied, and I'm going to put there multiply, we shift to the left. Okay, and now we're going to do division. So we'll start off with just a random binary number. Let's have a little look. So we'll keep the math simple just for this. So we're going to have a 16, a 2 and a 1. Okay, so that equals 19. Now, I've chosen that number on purpose because when you divide 19 by 2, you don't get a whole number. But watch what happens. Okay, so we're going to do the division. Everything shifts to the right. So we start writing the number again. Okay. We'll start from this side, so 0, 0, 0, 0, 1, 0, 0, 1. Okay? That number there is 9. So we don't get a fully accurate answer every time when you're dividing using this system, because actually 19 divided by 2 is 9.5. So we lose the half. So you do lose a bit of the accuracy, and that's an important point you might need to make in your exam. But the system works. Had we done it with the number 20 instead, okay, and I'm going to just show you that just here, had we done it with the number 20, or maybe, let's say we do it with the number 16, okay, just because it's even easier. Okay, so we'll do the number 16, divide it by 2, so we're doing the shift in the direction of the right, so we move it along 1, okay, and then if we just pop our place values on, what you'll see is, that we've got the 1, the 2, the 4, the 8, the 16, and 16 divided by 2 is 8. So you can see that the system works, it just doesn't always give you a fully accurate answer. So, in this clip, what we've seen so far is we've seen, I'm going to take the camera over now, as I said that I would do. Okay, we have had a look at the basics of the binary, denary and hexadecimal numbers. We know that binary has got 2 numbers. It's base 2, but it has 2 numbers. Denary, base 10, has 10 numbers. Hexadecimal, base 16, has 16 numbers. But because we run out at 9, we have to use some letters, A being 10, C being 12, and E being 14. You can work out the rest. F has got to be 15, hasn't it? We talked about converting from one number system to the other. And we said that when we were doing that here in base 2, okay, we write our place values on. Notice that the place value, the first one, is always the units column. It's the same in base 2, 10 and 16. Look, units column, units column. And then you're multiplying by, in this case, 2. So we go 2, 4, 8, 16 and so on. And then you're just looking to see where the ones are, and if you know the place values, you can work out the base 10 number. We then did 50 going in the opposite direction, and you remember that what I did there was I started at 32 because 64 is too big. That left me with 18, so I needed a 16 and a 2. We then had a look at how you do base 16 numbers, and we looked at how you can take a number like this one here, 74, in base 2, bring it over here, draw that imaginary line, split it into 2 nibbles, work out what this side is, 1, 2, 4, work out what this side is, 1, 2, 4, 8, 8 and 2 is 10, 10 is A in base 16, don't forget. That gives you 4A. And then we converted that and we checked and we said 4 times 16 is 64, 10 times 1 is 10, and it gets us back to our 74. So we know the system works. If you're not sure, come and ask. We then had a look at adding binary numbers, which works absolutely fine. We said to help us out, we're going to, I always write down the first 4, sometimes I do the first 5, just to remind me what the answers look like. 1 plus 1 is 2, it's written as 1 and 0. And then as we moved across here, it couldn't have been more simple. We were only adding 1s and 0s together, and the most you had to do was to carry a 1 onto another column. It was nice and straightforward. We then looked at binary shifts, where we talked about powers of 2 and how you work out how many shifts you do. And when you're multiplying, you're shifting numbers to the left. We started with the number 10. We shifted it 1 place to the left and it became 20. It was 1 place because 2 to the power of 1 is 2, and that's how you multiply by 2. And then when we divided, we shifted to the right, so we went from this direction this way. We saw that with some numbers you'll lose some of the accuracy. 19 divided by 2 is 9.5, not 9, but in some cases it works just fine. That's the end of this clip. If you've got any questions, do come and ask, and hopefully you found that useful as a quick reminder of how to deal with the different numbers.